Alright, welcome back. This is Thermodynamics II at South Dakota School of Math and Technology. We're up to homework 4. This is on fugacity. So, our first problem states, estimate as best you can the fugacity of benzene at 350 K and 25 bar. Okay. And so, what does that mean? Okay. Well, the first thing I have to do is I need to recognize it's a vapor fugacity problem. But after I do that, now I need to decide, okay, which approach do I need to use? Okay, well first I ask myself, is it pure or is it mixed? Oh, well it says benzene, so okay, that means it's what? Pure, yeah. So okay, it's pure. Now I need to ask myself, okay, do I have an equation of state? Am I steam? Or none of the above. So, am I given an equation of state in that case? No. Okay, well, is toluene, benzene. Is benzene steam? No. Okay, so it's none of the above. And when it's none of the above, I need to use the Lee-Kessler correlation tables, which says log of phi is equal to log of phi naught plus omega log of phi 1. Or if we're using the tables from Smith and Van Ness, which is on your cheat sheet, that says phi is equal to phi naught times phi 1 to the omega. Okay? They're essentially the same thing. I mean, you look, you have log rules, you look at the same thing. Alright. So, I've recognized it's vapor fugacity problem. I've recognized that I have a pure system, and then I'm a Lee-Kessler correlation table. Of course, as such, I write down my equation. Now what do? Okay, to look up those values, I need the reduced pressure and reduced temperature. So first thing I need to do is I need to look up all my constants. So Tc equals, Pc equals, omega equals. Well, I just go to my handy dandy book. Okay. And we've got 562.1, we've got 48.94, that's bar, and then we've got 0.212. Okay. So, now what do? Well, now we get reduced pressure and reduced temperature. So P reduced is equal to P over Pc. In this case, what is it? I have 25 bars my pressure. Okay, so 25 divided by 48.94. Well, that's about 0.5, but I'm betting I want you to be more accurate than that, but I don't have a calculator. So we're going to estimate it to be 0.5, but don't do that on your homework. Okay. Or the test. Okay. Temperature, reduced temperature is, so T reduced is equal to T over Tc. I said it's 350 K, and then we got that. So 350 divided by 562.1. Okay, let's plug that into a calculator just really quick. We get, I can get it up. We get 350, okay, so equals 350 divided by 562.1. Alright, I get about 0.63, 623. Okay. So I'm definitely going to need to interpolate on that one. So we'll do one example of interpolation, but we won't do a double interpolation. Okay. But on your homework, I want you to do the double interpolation. Okay. So what's the next thing I do? Well, Dr. Hadley's saying something about double interpolation, so I'm betting I need to do something with reading a table. Yep. So I go to my tables and I find out what it says. Okay. So let's say, now, okay, what if you wrote a code to do this for you? Well, all you would need to do is calculate these things and tell me what phi 1 and phi naught are. Okay, well my code doesn't spit out that, it just spits out phi. Well, but you can go into your own code and spit out, you can have it temporarily through a message box or debug.print or something. Spit out what phi0, phi1 are. But I do want to see what they're equal to when you're all said and done. Okay, but I don't. You can just say used interpolation code to do interpolation. That's fine. The other thing I want you to do is I do want you to be able to look up in the table the values correctly. So, of course, I guess if you have the code, if you just spit out, if you show this work and you spit out a phi, that's okay, because I'll assume that you wrote the code, you know how it works. If you know how it works, then you've done all this correctly already. So we'll settle for that. All right, but in any case, let's say I'm doing this by hand. I don't have a fancy code. So what I need to do is, for example, for phi0, and I'm only going to do it for phi0. Okay, so for phi0 equals, at tr equals 0.6, and PR is equal to 0.5. Again, I'm going to do double interpolation, so this is going to be a little bit more complicated in terms of what the work is shown. 5.5. So I've got negative 1.233, and at the same pressure, but at TR equals 0.65, I've got negative 0.951. Okay. And then I would interpolate based on that. Okay, I'm not going to actually do the interpolation, I'm just going to go through the steps of the interpolation. So in this case, again, my interpolation formula is, I'll waste that one because I'm not going to use that one. And I'm done with that stuff, so I'll use it. So I'm trying to find what phi0 is equal to at the actual reduced temperature I have, which was at 0.62 something. Okay. So I have basically x minus xi over x1 over x2 minus x1 times y2 minus y1 plus y1. Okay. In this case, my x's are my t reduced, and my y's are my phis. Okay. So I do 0.62 minus 0.6, 0.65 minus 0.6, negative 0.951 minus negative 1.233 plus negative 1.233. What's that going to be? Oh, let's just ballpark it as negative 1.05. Okay, just for argument's sake. Okay. So I get that, and then I'm going to get a phi1. Okay. And these are the log of phi0. So, log of phi0. That's right. Alright. We go to phi1, and again, I'm just going to ballpark things. Okay, doing the interpolation, it's about negative 1.4. So I plug those into here. So I have log of phi is equal to negative 1.05 plus 0.212 times negative 1.4. Where's 0.212? That's the omega. I erased it. Okay. Let's see here. That's about maybe negative 1.1. Again, I'm ballparking, and then, but to get it, I do 10 to the. So phi is equal to 10 to the negative 1.1. What's 10 to the negative 1.1? Oh, probably about 0.1 or something. We'll just say 0.1. Okay. It's close enough for government work. Okay, because the other question asks, what does that say about the system? So those are all the steps. So we wrote down our base equation, we found our constants, we found our reduced stuff, we looked up our phi naughts and interpolated as need to be, plugged it back in, and got a value, and made sure we didn't, we did 10 to them. Okay, but what does that say about the system? Well, I have to ask myself, how does that relate to 1, okay? Let's see here. Well, it's less than 1, and so if it's less than 1, what does that say? It says that the interactions are more attractive than they are repulsive. But 0.1 is a lot less than 1. So what this really says is these are really repulsive. Attractive. Meaning, at 350K and 25 bar, it could be a liquid. Does that make sense? Well, 350K, that's kind of, that's high, I'll admit that. But 25 bar, that's really high. That's a lot of pressure. So it's keeping it close together so it's attracted to each other. So that makes perfect sense. That almost says, hey, this is probably not a vapor, this is probably a liquid. But that's okay. It can be, fugacity coefficients, even though this is vapor fugacity, can describe liquids.